So in Chapter 6, we take a look at chemical bonding. Chemical bonding is the result of the interaction of atoms. When atoms interact, what we see happening is actually their valence electrons, as they come closer, are actually beginning to repel each other. Remember, like charges repel. But at the same time, those valence electrons are actually attracted to the positive nucleus of another atom. Positive, remember, because of the protons in the nucleus. How much these electrons are attracted to the other atom and how large these atoms are, how much electronegativity is involved, all of those things ultimately end up determining the type of chemical bond that is going to occur between the atoms involved. So we say that a chemical bond is the force of attraction that holds two atoms together in a compound. So there are different types of chemical bonds that we're going to talk about, and it always depends on what those valence electrons are doing. But no matter what they do, the bonding results in a lower potential energy because atoms are more stable than their individual atoms were. So if we look at this graph actually represents on the x the distance between the atoms that are bonding, and on the y a change in energy. So if we start over here on the right, we read this graph from right to left, which is a little weird, but we start with two separate hydrogen atoms. And as we move to the left, these atoms are getting closer and closer together. And you can see that the amount of energy is going down until we reach this place where hydrogen atoms have bonded together. And they have an approximate bond length of 74 picometers. Not that you have to remember that, but that seems to be the happy place, this balance between the pull of the nucleus of one hydrogen atom to the valence electron of another, and vice versa, and the repulsion of the electrons to each other. So we're down here where we seem to have arrived at the minimum potential energy that we can possibly have. And as we continue to get closer and closer together, we see it spike back up to very high energy, meaning that it is actually possible for those atoms to be forced together too closely, which would mean they would have even more energy than what they had as separate atoms. So ultimately, the bond length is determined by that balance between the attraction and repulsion. And so they will always be at their minimum potential energy when they have achieved that maximum stability. We're going to start by looking at ionic bonding. Ionic bonding is the type of chemical bonding that results from electrical attraction between oppositely charged atoms. So remember that ions are formed by gaining or losing electrons. So if we start with this example, we have sodium, which has one valence electron, chlorine, which has 7. If they get close enough together, the chlorine is actually able to take away the valence electron from the sodium, which is what sodium wants. So that's a good thing, right? But that leaves sodium with a positive charge. It now has more protons than electrons, and it gives chlorine a negative charge because it now has that one extra electron. The positive chlorine cation, or positive sodium cation, is attracted to the negative chloride ion, and that attraction then is what forms this ionic bond. So ionic bonding always results from the transfer of electrons. We have to always have a giver and a taker. An element willing to give up electrons, another element wanting to gain electrons. Covalent bonding is a little different. Covalent bonding occurs when neither one of the atoms is willing to give away its valence electrons. So this happens when we have valence shells that are nearly full. We don't have a giver, we have two takers. So since no one's willing to give, they end up sharing. So covalent bonding is bonding between two nuclei that are sharing one or more pairs of electrons. So by doing this, we can see that carbon, for example, allows 2 of its electrons to be shared, giving each one then 5. Ultimately, carbon's going to end up needing more than that, but it is getting closer and closer to stable in doing so. How equally shared these electrons are ultimately determines if we have a polar or a nonpolar molecule. When the electrons are shared equally between the two atoms, we call that a nonpolar bond. Nonpolar meaning no charges. When they are not shared equally, because one atom has a stronger pull, a higher electronegativity than the other atom, the electrons spend more time with that atom and we have a polar bond, which means we have a slight positive and a slight negative charge. So if we look at these 3 different types, first we had ionic. Remember that ionic is the complete transfer of electrons. It results in a positive ion and a negative ion. If it is covalent, it is either polar covalent or nonpolar covalent. In polar covalent, we have a slight positive and slight negative end because the electrons are spending more time on one end of the molecule. If it is covalent but the electrons are shared equally, then we say we have a nonpolar covalent bond. We can determine whether it is ionic, covalent, and if it's covalent, if it's polar or nonpolar, by using electronegativity difference. This chart of electronegativities would allow us to do this. Ultimately, all you have to do is find literally the difference. So subtract the larger from the smaller and find out if the electronegativity difference is greater than 1.7. If it is, we would say that's going to form an ionic bond. If instead the electronegativity difference falls between 0.3 and 1.7, that's a covalent bond, but specifically a polar covalent bond. They're not playing nice. They're not sharing those electrons equally. And if the electronegativity difference is very small, less than 0.3, then they are sharing very equally, and we say they are nonpolar covalent bonds. So for example, if we know the electronegativity of sulfur to be 2.5, and the electronegativities of hydrogen, cesium, and chlorine to be 2.1, 0.7, and 3.0 respectively, which one of these is going to be the more electronegative atom? Well, sulfur is more electronegative than hydrogen at 2.5 versus 2.1. It is more electronegative than cesium at 2.5 versus 0.7. And it is less electronegative than chlorine, which has an electronegativity of 3.0. We can figure out the kind of bond that it's going to form by doing the subtraction. So we take our larger minus our smaller, so we always have a positive answer. 2.5 minus 2.1 is 0.4, so slightly above that 0.3 cutoff, so that is a polar covalent bond. Cesium would be 2.5 minus 0.7 or 1.8 electronegativity difference, which is going to be an ionic bond, and chlorine, which would be 3.0 minus the 2.5, which is a 0.5. So chlorine bonding with sulfur would also be a polar covalent bond. It's very straightforward, very simple. If ionic compounds form, it is the result of bonding where we have positive and negative ions. Most of the rocks and minerals actually in the Earth's crust are the result of ionic bonding. Table salt is a great example. Table salt is sodium and chloride ions in 1-to-1 ratio. It is necessary when you work with ionic compounds that the positive and negative charges cancel out. So since sodium has a positive 1 and chlorine has a negative 1, they can cancel out with a 1-to-1 ratio. When these ionic bonds form, the resulting compound is called an ionic compound. So an ionic compound is composed of positive and negative ions that are combined so that the numbers of positive and negative charges equal. So the overall charge of the compound itself is 0, even though it's made up of charged particles. Some properties result from this. Most ionic compounds are crystalline solids. In fact, many of them are white crystalline solids. Some of them are very colorful crystals, but many of them are white crystals. A crystal is a three-dimensional network of alternating positive and negative ions. And these positive and negative ions are attracted to each other because opposites attract, of course. But what we have to remember is that in a drawing, it may look like there is only one ion to the left and another ion to the right, maybe one above and another one to the other side. That this is happening in 3 dimensions, that ions attract each other in many ways. So depending on the size of the atoms that are combining, the size of the ions that are combining, the ratio in determining what the crystal is going to look like is going to be determined not only by charge, but also based on the size of those ions, because they can only get so close to each other because their electrons are ultimately repelling each other as well. And we saw that in the video. Some things have a 4-to-1 ratio in their crystal, others have a 6-to-1, and so on. Ionic compounds, because they are not simply made up of individual ions in groups that we would normally call molecules, they are instead many, probably millions of ions packed together in this structure. We can't say that it is a molecular compound. Instead, we have to describe those little particles a little differently. The chemical formula of the ionic compound is not representing what we would have if we were to make a molecule of an ionic compound, because we can't make a molecule of an ionic compound. Instead, it is giving the simplest ratio of the ions. So it is telling us how many positives for each negative in order for it to be neutral. We call this a formula unit instead of a molecule. So with ionic compounds, we have formula units. Formula units are the simplest collection of atoms from which an ionic compound's formula can be established. In other words, it is the simplest ratio of positive to negative. When ionic compounds form, as they achieve their position where they have that balance between repulsion and attraction based on the size, we get an orderly arrangement called a crystal lattice. So these attractive forces, as I mentioned, are going to pull together oppositely charged ions. At the same time, there are repulsive forces that are going to exist between those like charged ions, and they're going to be pushing away from each other. When we have this balance, then we find the distances between the ions, and we have ultimately the ability then to figure out the pattern of the ions arrangement in the crystal. When they achieve this structure, there is energy given off as they come together. That energy is called lattice energy. And lattice energies are dependent on what is combining and how electronegative those atoms are that are involved. So you can take a look at the very small lithium and fluoride coming together and giving us 1,036 kilojoules per mole of lattice energy, but larger cesium and iodide atoms, if they were to bond together, would give us only 604 kilojoules per mole of energy.